Right, so well, let me try to wrap up from what we observed from this simulation. Uh, where we look at two cases of the standing wave. Okay, this is the case 2 and 3 that we just talked about on the animation. We're not going to talk about what we observed for the first case, that when the wave travel to the same direction. Okay, only standing wave. For both case of standing wave, two fixed end string and one fixed end or loosened end string. Okay, let's start from the two fixed end. That is the third case that we just mentioned about. You see that both end of the string must be fixed. Must be fixed means that there are two nodes at the left and at the right. That is, and one loop. Let's count the number of the lambda. One loop means that half of the lambda, right? Two loop means that lambda, and three loop means that 3 lambda divided by 2. One loop means this is one loop, right? When you get two loop, this is one lambda. Okay, nothing complicated. And both and all, let's say, equal to L. You see that the lambda vary because we change the frequency, right? They are the same string, so the wave speed should not be changed or should not be different. So to get the different mode, so you have to change the frequency. Let's try to relate this to the frequency of the wave that we're gonna have to put in. For the first case, for the first harmonic, so in this case we put number 1 into the animation, right? It's number 2 and number 3. Okay. So v equal to f lambda. So lambda is, okay, let's say v equal to f lambda. So lambda is v divided by f. So let's try for the first case. So we get L equal to v divided by 2f. So you get f1, we call it f1, equal to v divided by 2L, right? This is for this case, fundamental frequency of the two fixed end string. Okay, the second one, when you say, okay, lambda, my L equal to lambda, and lambda equal to v divided by f, I will just do this quick. So I can say that f2 is v divided by L. And the same for the third case. Okay, you get L equal to 3 lambda divided by 2. I'm quick doing this. This is L, sorry. It look like N somehow. But this is L. Sorry. Okay, for the third case, we do it quick. So we get f3 equal to 3v divided by 2. Okay. Oh, so that's correct. Okay, it's equal to 3v divided by 2L. So we get equation for each case. Let's try to make it all of them to one simple form. So if I put 2 in front of V and 2 in front of L for the second harmonic, what we can get for the common form is that Fn equal to Nv divided by 2L. And this is for two fixed end case. You can see that N can be any positive integer, right? Can be start from 1, 2, 3, 4, 5, and so on. This is for the case of two fixed end. The resonance frequency can be 5. This is harmonic, number of harmonic. Okay. You can also call the first harmonic as the first harmonic, or you can call it fundamental frequency or whatever you like. Okay, for the one fixed end, like I did on the simulation, I put number 1 and I get this structure. I put number 3 and I get this structure, and I put number 5, I get this structure. Why it must be only odd number? Okay, for the fundamental case, or the first case, I could say first harmonic. This is like half of the loop, right? So remember, this is one loop, and if you cut it half, so it is only half, and this half of the loop equal to lambda divided by 4. When you add one more, you get lambda divided by 4 plus lambda divided by 2, and this is become 3 lambda divided by 4, and this one I can say this is 5 lambda divided by 4, because you add one more loop in. Okay, and all of them equal to L, equal to the length of the string. When you try to make this the same way as you did for the 2 fixed end, and okay, this is for the case of 2 fixed end, alright? You do this for the 1 fixed end or losing end string. You get f end equal to nv divided by 4l, and only number that represent this n is the odd number or odd or integer 1, 3, 5, 7, and so on. This is for the 1 fixed end or losing end string. Okay. What else I should talk about is that, okay, this is for 2 fixed end, alright, and you get this form. Although I didn't talk about the sine wave before, but I would like to wrap up the idea of the resonance of the sine wave in TILF, or also in this chapter, okay, because they get very similar to what we found on the string. Okay, let's say we have a sine wave, and there are 2 cases that you can get the resonance of the sine wave in the TILF. So one is the closed TILF. Closed means that one end of the TILF must be closed and must be node. And the open TILF, in this case, it must be open both sides. And at the end, you get antinode. So this is antinode. This is antinode. This is node. Okay. Okay. I should try to compare this with the case of string. So you see the fixed end, 2 fixed end, 1 is node, right? The other also node, right? Okay, and 2 fixed end string, you get this is node, and the other is antinode. Okay, this is node and this is antinode for the closed TILF. Okay, all right, that seems like okay. You compare the closed TILF with the losing end or 1 fixed end string. You see they have exactly the same structure when we change from the first possible shape to the second possible shape. So they both get the first, third, fifth, seventh harmonic. So they get to the same formula for each harmonic, each possible harmonic. Okay, this is for, so let me conclude this equation. So Fn equal to n v divided by 4l, and n is only the odd number. This is for 1 fixed end and sine wave in closed TILF, 1 fixed end string and sine wave in closed TILF. All right, for the length of the string L and the length of the tilde also L. This is two different cases, but we can analyze getting the same equation for both cases. Then we come back to the case of open tilde. You see that it's different if you compare this with the two fixed end. You see this is two fixed end. You get both side node, right? And in the middle you get antinode. But for the open tilde, you get both side antinode, and the middle you get the node. It's pretty different, but one thing you might see that if you count the number of waves inside the tilde, they are the same in each harmonic compared to the two fixed end case, right? You get this is lambda divided by 2. This is lambda, and this is lambda 3 lambda divided by 2, and so on. They are the same, although the number of node and antinode are not the same, but if you want to analyze them, okay, using mathematics, okay, trying to make a equation to find the different resonance frequency, you get the same equation. Okay, so let's conclude this. So this equation Fn equal to n V divided by 2L for n are positive integer 1, 2, 3, 4, 5. This equation can be used for either the resonance of or the resonance or the standing wave on two fixed end string, or the sound wave in open tilde. Okay. Yes, that actually is okay. Let's try some exercise. So standing wave of the fourth harmonic is generated on a string of length 1 meter fixed on both ends. So this is the case of fixed end, two fixed end, let's say. If the oscillation frequency is 5 Hertz, what is the wave speed? And also, if the mass of the string is 100 grams per meter, what is the tension of the string? So first, I'm gonna write, this is fourth harmonic, right? Fourth harmonic means that you get one, this is for both ends, right? So you add one more, you get second, one more, get third, fourth should be like this. And this is for loop equal to 2 lambda, right? Or you can say that this L equal to lambda is V divided by F, right? And in this case, you can say that F4 equal to 2V divided by L, or you can actually record the equation, right? You can say that okay, Fn equal to NV divided by 2L. So you can say Fn equal to NV divided by 2L, and then you put N equal to 4, then you get 2V divided by L. So you can try to memorize the equation, or you just trying to analyze this by yourself is also fine. Okay, so you get this. You know this is 5, right? This is F4, and you get L equal to 1 meter. This is L. You can find the wave speed. So this is 5 Hertz. Let me rewrite this. It will be L multiplied by F4 divided by 2. This is like 1 5 and divided by 2 is 2.5 meter per second. Okay, this is the answer for A. And if the mass of the string is 100 gram per meter, what is the tension of the string? So we equal to square root T divided by mu. Let's go to the very first slide. And you want to find the tension, so you can say that the tension is V square multiplied by mu, right? And you get V of 2.5 square is already in the unit of meter per second. You don't have to change, but for the mu, yes, you have to really get this to SI units. So in this case, 100 gram is 0.1 kilogram per meter. Okay, and this should be 0.1, right? So what you get is 625. Okay, 6.25 multiplied by 0.1, so this should be yes, 0.625 Newton. Right? Am I wrong? No. Well, actually, the value is not so good. But anyway, this should be fine. We just get the correct answer, right? Okay, this is quite similar. I will get you to try by yourself. What else we should try? Okay, this is for the case of standing wave. A sinusoidal wave of amplitude of 3 centimeters is generated at a frequency of 2 Hz and travel with the speed of 1.8 meters per second on the string of length L. The superposition of the incident wave and reflected wave on the fixed end generates a standing wave. Okay. Write the function if you still remember. And okay, this is also using psi function of the component wave, so you can rewrite the wave 1 y1 xt, or I can say this is like incident, so yi xt is 3 centimeter of amplitude, and psi k is, we only know the wave speed, right? And we know the frequency, so we have to find the lambda to get the wave number. So v equal to f lambda, and lambda is v divided by f. You know that v is 1.8 meter per second and frequency is 2 Hz, right? So this is like 0.9 meter. Okay. Well, you're gonna have to find k. K is 2 pi divided by 0.9. Okay, I'll just write it directly like this. So like 20 pi divided by 9. Okay, x, and it's travel with the speed of, let's say, positive speed. Okay, because it's incident, we can just say, okay, this is incident. We're gonna keep this wave travel to the positive x, so this should be negative psi, and omega is 2 pi f. So we know f is 2 Hz, 2 pi is 4 pi or t, like this, right? This is a function, and you can write the reflected wave as, actually they should have the same thing, psi 20 pi divided by 9x minus 4 pi t, and of course you should get the phase difference, because this is to fixed n, right? This should be pi. And okay, I'll not show how to find this again, but you can actually use the solution from here. Okay, from here it's minus 2ym cosine kx, minus 2ym, right? Minus 2ym cosine kx and psi omega t, right? This is y plum xt. Okay, you can put the ym in. You know that ym is 3 10 to minus 2. Put the k in and omega in, you get the complete function. Okay. Oh, sorry, this is the wrong one. Okay, I get it. So we put y plum xt equal to 2, okay, minus 6 10 to minus 2, and this will be cosine kx psi omega t, and this is a function of the resultant wave, right? Okay, and the answer for A will be this two. Okay, and for the C, what is the length L at that correspond to the first, second, and third harmonic? What is that? You know that in this case you fix the lambda, right? If you want to get the first, second, and third harmonic, you have to change the length of the string, okay? Because the lambda already fixed by this amount, 0.9. You know, lambda is 0.9 meter, and this is the case for two fixed, and you know that the first harmonic is like this, second is like this, and the third is like this. Okay. So for the first, lambda divided by 2, or let's say L equal to lambda divided by 2, right? And this should be 0.45 meter. The second harmonic, you get L equal to lambda, and this should be 0.9 meter. And third harmonic, this actually L equal to 3 lambda divided by 2. So what you get is 1.8 divided by 2. Sorry, this is wrong. No. No. Okay. 2.7 divided by 2. So this is become 1.35 meter. Am I wrong? No. Okay, and that is for exercise 6. Not sure if we need to do anything on this. It might be a bit different. Okay, let's try exercise 7. Organ pipe A with board end opened and has a fundamental frequency of 300 Hz. The third harmonic of organ B with one end open has the same frequency as the second harmonic of pipe A. So this pipe A is board end open, and the fundamental frequency of this case is look like this, right? Oh, sorry, my hand is not so. Okay, this is the first harmonic of pipe A. Okay, F1 equal to 300, right? Hz. Okay, and pipe B, the third harmonic of pipe B will be for the one closed end or one end open. It would be the same. We get third harmonic should be something like this, right? Because the first harmonic should have only this part, right? Okay, this will be the third harmonic. Oh, sorry, I'm wrong. The third harmonic, not the third possible mode. This is also had the same. Okay. Okay. Am I wrong? Put it like this. Okay, the third harmonic. Third harmonic means that the second possible mode. So it should be like this. Okay. This is third of B. That has the same frequency as the second harmonic of pipe A. Okay, let's try. So this is the first harmonic of pipe A. So the second harmonic of pipe A should be 2 multiplied by 300 Hz. If you go back to that equation, you will know that it just, the first, if you want to find the second or the third or so on, you just put the number of the harmonic multiplied by the first harmonic's frequency, and you get it. And this, in this case, is 600 Hz, right? This is the second harmonic of the pipe A, all right? And this equal to the third harmonic of organ B, right? And the third harmonic of organ B, what? Is okay. This should be the case for 3 multiplied by. Let me go back to that equation actually. I don't want to analyze from the beginning anyway. Just try to use the equation that we already have. So this is NV divided by 4L, right? Okay. This will be NV divided by 4L. And this L is something that we want to find, right? Okay, I think one thing is missing here is the wave speed, right? We're gonna use 343 meter per second because we don't have, we cannot find it. Okay, in this case, L gonna be 4 multiplied by 600. Sorry, this is wrong. Okay, L gonna be 3 multiplied by 343 divided by 4 and 600. This will be the answer. This is LB, or the length of pipe B. And what about the length of pipe A? The length of pipe A are also the same. Because we get the same, we can choose one of them, let's say, or the fundamental frequency. See that 300 equal to, again, this is gonna be V1 multiplied by V divided by 2L, right? You can check this is correct for the open tube. Of course, this is NV divided by 2L. Okay, and when you get the first harmonic, that should be, this N should be 1, right? So then you get LA equal to 343 divided by 2 multiplied by 300. Okay, I will not calculate the exact value, but this is the answer for this one, and this is the answer for this one. Okay.